So here we now finally have our 4 fundamental equations of thermodynamic variables. Each of them represents an exact differential equation. And what does this definition or this term exactness actually imply, and how can we use that to derive the Maxwell relationships? Let's consider a function f. And this is its expression. It is a function of 2 variables, x and y. We can now determine the partial change of f if I change variables x and y just in x by considering the partial derivative or the slope of how f changes with x, while I'm for now just keeping y constant multiplied by the extent of this change. So in other words, if I perform the integral, just visually see what we're busy doing. I have f as a function of x, and for this line, this slope, this represents that equation of the slope of the change. If I am going to integrate between x1 and x2, the area below that slope will give me that partial change in f as a function of x. But of course, since we are interested in the total change in f, we also have to add the partial change in f with y while I'm keeping x constant. But now, since I already changed to x2, when I evaluate the slope of this equation, it must be where variable x is equal to x2. So now I will have f as a function of y, and some other slope will define that change between y1 and y2, and I can get that area there. And just remember that for this entire graph, x is equal to x2. Each of these slopes are also represented by an equation that is in turn a function of our 2 variables x and y. We can now give them new names. Let's call this equation m. The y is there, subscript y, just to remind us that when we defined that slope, y was considered to be a constant. And for this partial derivative, we use the symbol n, just a reminder again. For each of these equations, we can now take another partial derivative. So where we kept y constant, we can now take the partial derivative of that resultant equation to y, while now we keep x constant. If we look at that equation, that will give me a value of c. And if I do the same for equation n or function n, but where I kept x constant, I now take the partial derivative to x while I keep y constant, I also get an answer of c. And what I've just proven is that our function f, or the df function, is an example of an exact differential equation. Since what we've proven is that it doesn't matter in which order we perform the derivation, whether it's first to x and then to y, or first to y and then to x, the resultant slopes, final slopes, is exactly the same. And that is the test for exactness. What this implies is if I am now interested in calculating the total change in f with a change in these 2 variables, it doesn't matter whether I perform the change in x first while I keep y constant when I consider the slope of how f changes with x, and then when I evaluate the change with variable y, I must remember that x is constant, but it is now at state x2 when I consider the calculation of this slope in this part of the differential equation. We must, if the equation is exact, therefore get exactly the same result if we perform this part of the change first, and now x is at state x1 when I evaluate the slope. So this is done first. Now I consider the change in x while y is at state 2 because I already changed, from y1 to y2. Since all our fundamental equations are a relationship between thermodynamic state variables, each of these differential equations is an example of an exact differential equation. The next video, we'll see what's the implication for that and how that results finally in the Maxwell relationships.